I'm going to give a presentation today on just sort of general overview of CO2 geochemistry. I'm going to talk about I'm going to talk about your first few reactions that you can anticipate when you inject CO2 into the subsurface. It's mainly going to be focused around CO2 water mineral reactions and your sort of generic approach to modeling. And then I'm going to talk about near well bore dryout. I'm focusing mainly on things that have implications rather than just a general overview of geochemistry. And yeah, it's inorganic chemistry. I'm not a petroleum geochemist by any measure. As soon as there's any hydrocarbons involved, my brain shuts off, but I can always try my best. Chris, could you go to the next slide, please? Sure. I just give a quick overview of OPC, the company that I work for. We're a subsurface consultancy going for about 35 years. It'll be 35 years this September, actually. We've worked in more or less every country for a range of brilliant clients, and we've done a huge amount of projects. We also provide consultants and software and training. I mean, a lot of people know OPC is a well testing consultancy, but we do the whole subsurface suite. And in the last maybe 5-10 years, quite a lot of CO2 projects. Next slide, please. We've got offices in Houston, London, the North Sea, Norway. Some of these are in slightly odd locations where they don't quite correlate to, but also in the Middle East and Kazakhstan. Next slide, please. So who am I? I think it's better to start with who I'm not. I'm not Indiana Jones, despite the photo, which is taken in Almere, where the same set was filmed. My background is in geoscience. I've got a master's and undergraduate degree in geology. I've got a nice photo there in the bottom right. That was me in India looking at the Deccan Traps. I did my master's at UCL in fluid rock CO2 interactions with somebody called Professor Eric Olkers, who was one of the sort of leading CO2 geochemists. First looked for basalts because that's what my research focused on originally. I worked with Aramco and Carbfix doing a project in Jazan. The work was published, and since I did my master's and I met my boss in the pub, weirdly enough, and he gave me a job, I've been working with OPC for the last 2 years, and I've done roughly about 10, 11, 12 CO2 storage projects for OPC, varying from engineering, geoscience, geochemistry, quite a holistic approach to our projects, and I give my input where required. Next slide, please. And again, so let's talk about our expected subsurface CO2 reactions. So let's just talk about some governing principles, first principles, as it were. When you inject CO2 into the subsurface, it's going to react or interact with the water, and there are certain controls on how quickly that happens. The first one is the solubility. So this is what we're mainly concerned with the geochemistry, because when the CO2 dissolves in the water, i.e. to make fizzy water that we like to drink, it creates carbonic acid. And what controls that is generally, you can see in the left diagram, the pressure and the temperature. This is calculated in frequency using the Peng-Robertson equation. Generally, CO2 dissolves more readily in colder water at higher pressure. There's also an inverse relationship between the salinity of the fluid. So the more saline water is, the less CO2 generally is going to dissolve in it at certain rates. It slows down or affects the absolute amount of CO2 that you can store in water. The implications, well, it's important to understand because it will describe the rate at which carbonic acid will form. And we see there in the bottom equation here, is CO2 plus water in an aqueous solution creates H2CO3 aqueous plus H plus ions, which basically the greater the amount of H plus ions in the solution, the greater the acidity of the solution. We can go next slide now, Chris. See, we're trying to hide this, but it's not really working. I've got a lovely photo on the right here that every geologist will recognize. So if we now include CO2 and water and we introduce rocks, so we form carbonic acid through the dissolution of CO2 in water, and what will ultimately happen is a low pH CO2 charged fluid will cause the dissolution of certain rocks or certain minerals within rocks, some more readily than others. Classic one here, you've got calcium carbonate, CaCO3, in the presence of any acid. You do the acid test. Is it calcite? Is it quartz? No, it's calcite because it dissolves in hydrochloric acid. You get the dissolution of the rock. Now, if you imagine you dissolve a certain part of a rock into a fluid, and we just treat this aqueous fluid as one big thing, it is saturated in terms of different mineral phases. So, if you dissolve one, you can precipitate another, not necessarily absolutely, but if you have certain bits, so say we dissolve CaCO3, you'll have some calcium in the aqueous solution that could form back into calcite at a different pH to form a new mineral. And that's what we talk about, the precipitation of others. And that as a process is largely thermodynamically confined. New minerals will precipitate based on temperature and pressure. For example, calcium carbonate will form with the right constituent parts at any sort of temperature over 30 degrees, and isn't really that related to pressure. But for example, iron minerals are very hard to form because, well, are very easy to form because iron is extremely insoluble in water. So it wants to fall out of the aqueous solution and turn into a mineral. And yeah, and I said the rate and extent of the dissolution will depend on the amount of rocks that necessarily will buffer the system. So yeah, that's the sort of first step. Next slide, please. Now, if I talk about the sort of your controls, what you're actually interested in, and I'll tell you why you're interested in the pH in a reservoir soon, but I'll talk through some step reactions and maybe put some numbers and try and discuss the sort of time frame for reactions. So you inject CO2 into your indigenous fluid in the reservoir, which can be the pH between 5 and 7, depending on the salinity. If it's brackish, be more closer to 5. If it's quite salty, be closer to 7. If it's completely saturated with halite, as it would be near a halite cap, it'll be closer to 7. But these vary greatly depending on a load of different characteristics. So CO2, water, forms carbonic acid pretty quickly. This will happen in hours to days, but that is the control on there is the temperature, the pressure, and the salinity as discussed. And certain minerals, if they exist, will readily dissolve in the CO2 charged water at low pH. A classic one is calcite. These are common across sort of any carbonates that are common across any sands or any sort of saline aquifers or any depleted fields, for that example. That will cause the dissolution of that mineral. When you dissolve that mineral, it will, one, absorb some of the CO2 by taking it in, but it also will increase the pH of the fluid. So that will then, you see here in the graph, so we've got rate 1, the pH drastically drops from around 6 to roughly a bit above 3. We dissolve the calcite, it then increases the pH further, and then we might also dissolve silicates, which takes usually a lot longer, just due to the rate of reactions and reactivity series. I could go into more detail about that if anyone has any questions about the controls of what affects the dissolution of different minerals in rocks. But generally, as a bulk, if you've got calcite in a reservoir and you're injecting CO2 into it, it will dissolve quite quickly. But things like quartz, they're very, very unreactive in the presence of CO2. But anyway, when you dissolve the calcite, it will increase the pH of this fluid, and you may then get the formation of new minerals, which also increase the formation, pH of the fluid. So you have this sort of, we call it a swing reaction. pH goes straight down, and then the rock buffers the fluid and it goes back up. And then as the pH goes up, the reactivity of the rock is reduced. And so you reach equilibrium relatively quickly, but we talk about geological timeframes. When you're doing CO2 injection modeling, you have the option to turn on the CO2 rock water interactions. You generally just don't see things in the reaction in the time frame that you are concerned with. So generally it's not worth doing in full field modeling, but for specific projects, some of the ones I've been doing recently, it can be very important to have a look at this, at least to do a first sort of check study, as it were. Next slide, please. Let's have a look. So I'll just talk about modeling here and how you actually have a look at doing these reactions and doing a study. So yeah, we do equilibrium or batch modeling. So point by point by point, it's not dynamic, it's static, predefined. And there's various reasons for that, because if you just throw everything at a simulator, I say there at the bottom, the driver of the software is far more important than the tool itself. We use this thing called FreakC, which is basically, it relates a database of how minerals and different phases or gases interact with one another at various temperatures and pressures, and it will describe the rates of those, but it won't, you can make it do it kinetically to calculate the rate, but that requires things like surface area. So you can, it's a very powerful tool, but you imagine we have to, we have to describe the conditions that we want, and we have to understand the implications of that. So if we have a model, or we want to understand what's going to happen when we inject the CO2 into the fluid at the pressure and temperature, we take the fluid chemistry, so a water sample with all of your total dissolved salts, your anions, your cations, and then we're going to need the pressure and temperature. It has a massive effect on the rate of which reactions will take place, or if they will take place at all. I say here your XYZ, so you could take your K layer, for example, in a simulation model, and you know your pressure, temperature. You also know your PCO2. PCO2 is your partial pressure of your CO2. And you also want to understand the impurities that are present as well, because they may have a role in the chemistry. Generally, you can tell how a system will react if it's going to be anoxic or oxic just based on a water oxygen balance, and then you can anticipate, for example, if you'll get the dissolution of pyroxene or sulfide minerals, which can be, of course, the presence of sulfuric acid can be a big implication if you're trying to design where your well is going to go and how you want to cement and case it. But I'll talk about this a little bit more later in the presentation. So we've got our indigenous fluid, we've got our pressure and temperature, we've got a partial pressure of CO2, our mineralogy, and you can throw that all together and equilibrate them all together just as an initial reaction to see what happens, what the pH does, and you can step it out so you know what happens generally in a rough time frame. And yeah, you get your expected equilibrium water chemistry, and I say they're the SI of mineral assemblages, which is the saturation indices. So if it's you have positive and negative numbers which relate to if something's supersaturated or undersaturated, it means if it's going to dissolve or precipitate in that fluid. And yeah, again, the driver of the software, I mean, anyone can use Freaksy. It's quite simplistic, it's nicely easy to use, quite simple, but understanding what is analogous to the real world is much more challenging in terms of geochemistry, because the level of information, and if I show the next slide, that you get out of a modeling software like Freaksy can be quite hard to disseminate. I've taken two screenshots here. One was the left one from my master's thesis, which looks a lot nicer from the right one, which is one I've just taken from a recent project where we've been running some batch reactions to anticipate what's going to happen in the subsurface. And sometimes you get the state of too much information that there's too much information to disseminate unless you really know what you're doing, and I wouldn't claim to. I just kind of know how to run the software and roughly what might happen. You need to have been doing this for quite a long time to understand the implications of it, and sort of people that we work with, geochemists, 20-30 years experience, it definitely helps to know what will actually occur. And what I mean by that is, what is realistic, what realistically are you going to dissolve, and what realistically are you going to precipitate, because this will take every possible mineral under the sun and every possible mineral that you can create, and will tell you if that will happen or not. And of course, there's certain constituent parts in your rock that won't dissolve, and that depends on how the minerals are arranged. If you've got alterations, albite, for example. Anyway, next slide, please. And you'll have to keep me, Barney, you have to keep me on time, by the way. Implications. So if a rock does not buffer a CO2 charged fluid, for example, what I mean is there's no calcite or there are no minerals that will readily dissolve, the implication is that your pH of your fluid will remain around 3, potentially up to 4, but it's all log units, so it can vary quite greatly. The implications for the well design and the cement design, even far away from your injector, is that you're going to have to basically gold plate it with 25 chrome, which of course is costly, but you need to understand if you're going to need to or not, and I can help that with on projects that we've done, and that relates to your conate water saturation, because the weird thing to understand is that about half of the water that you displace in the rock, as you propagate a CO2 plume, will remain in place because of the natural sort of stickiness of it. And so if CO2 is anywhere in your sort of reservoir, it generally will be there in quite a high concentration, and it will react with that water. Another thing to understand is that if you're injecting CO2 into sort of fresh or low salinity fluids, you have the potential to have an increased storage capacity, as the relationship between CO2 dissolution and salinity is clear, that the less salinity you have, the more you can dissolve in the fluids. You can take that space up rather than just relying on the compressibility of brine, if you do when you're injecting into a saline aquifer. And the last bit here is that all systems are rock dominated or buffered. That means that the volume of space in a meter cube is dominated by the rock. So no matter how much CO2 you can put in the ground, the rock will always win, as it were. It just depends on the time frame that you're concerned with. Okay, next slide, please.
Max,
Yes,
that's 15 minutes now.
that's
So
15 minutes. Perfect. I won't talk about near wellbore dryout then.
well, you can do, if you want to rattle through in a few minutes, and then we can take then we go straight on to Chris and take any questions for you at the end.
Okay, perfect.
And for the audience, I think we'll aim to finish at 13:35 rather than 13:30, because we got off to that slow start.
Okay, well, I'll try and run through it quickly then. Okay, next slide, please, Chris. And I've made some diagrams, so it should be pretty easy to go through. We can rush through here. So I've got a diagram of a well here. You put your CO2 down the well, it goes into the saline aquifer. Our saline aquifer is made of water and salt and various other constituents that we're not really concerned with here. Next slide, please. Next slide, please. There you go. So we sustain our injection, we displace fluid, we displace our salty water, and the plume extends over time, and you have what we call a drying effect. If you take a bowl of salt water and you leave it outside, especially on the last couple of days we've been having, you're left with salt. Essentially, and that is more or less what happens, varying magnitude and scale, when you inject CO2 into a saline aquifer. Next slide, please. Now, I'm just going to focus, we don't have too much time, I think I've just talked about that, on the implications of it. Next slide, please. And there you go. So we have our drying front, our flooding front, but this is on a big scale, of course, where your CO2 plume propagates, but also, if we go on the next slide, on a much smaller scale, just between pores and grains, that essentially your water that is stuck between the pores, the salt will be naturally drawn to your drying front, and it will escape the water and it will precipitate as a salt. Next slide, please. And I can show you from an experiment here. There's an actual salt crystal basically forming in between your brine and your CO2 and your grain. Now, the problem with salt crystals is they take up space, and when you're injecting CO2 into a reservoir around your wellbore, you want as much space as possible to inject your CO2, because you want to manage your injectivity, your pressures, etc., etc. Next slide, please. There we go. So what can some of the problems of basically filling up your pore space and your space around your well? You can have a permeability decline, you can have a porosity decline, and ultimately then that leads to an injectivity decline, and if you're really unlucky, a complete loss of injectivity and potentially poor well performance. Now, you've spent 20, maybe 30 million if you're offshore, less if you're onshore, and then your well isn't doing your 1 million tons per year, and you can be quite upset about that. So it might be good to have an understanding of how you can resolve this. Next slide, please. I've actually got some 2D modeling here. We can go there. That's after 100 days. This is the permeability decline modeled in the endurance field offshore in UK. Next slide, please. At the first 1,000, 2,000 days, you see, wow, that's actually quite a drastic decline in permeability. If we go next slide now to 5,000 days, it's quite dramatic. Now, you can see, especially around that wellbore area where you're going to put all of that fluid through, and you want to keep your pressure, well, as low from max frac as possible, that might be quite difficult. Well, as the CO2 is less buoyant than the surrounding fluid, it goes up vertically, but you see that real drying effect around there and the salt precipitation. Now, this is just anticipated. This was done in 2014 with the help of OPC for the Northern Endurance Partnership, but how good is this? I'm not sure, but this is one way of modeling it. This is using tough. Next slide, please. I'm very conscious I don't have a huge amount of time, so this is my last one. We'll be happy to sigh relief. Here's taken from a presentation by Equinor. Now, Here we have our flowing gauge pressure, shut-in gauge pressure, flowing bottom hole pressure, and shut-in bottom hole pressure. Now, you can see we start at around 230 bars of pressure, and then about 290 for the top section. You drastically increase the pressure in the bottom hole of the well, and that's anticipated by early injectivity problems related to salt dropout. Now, it also says here, resolved by injection of MEG. I can't quite remember what MEG stands for, but I think it's methyl ethylene I can't quite remember, but essentially you're injecting something to dissolve the salt and move it away. But in this case, the continued injection and the resolution of the MEG wasn't good enough, and essentially the pressure continued to increase, and to the point where the well just couldn't perform the way they anticipated, and it ultimately had to, thank you, glycol, had to be shut in, and then injection was restarted. But you get too close to your frac pressure right at the top there, which is that red line, and you get to your frac pressure, well, the regulator's not happy because you might start fracturing a rock, and that might have an implication for the well and your sealing mechanism. Next slide, which I think is me just saying thank you for listening. I hope can happy to answer any questions.
Thanks very much, Max. No, that's really interesting. There's certainly a question in the chat, but I think we will hold fire on that and go straight on to Chris's, and then we'll cover all sorts of questions at the end.
Thank you.
Yeah, appreciate that. A good starting point for leading into Chris's presentation.
Yes, sorry, I'm battling with the floating Zoom controls that keep on popping up every time someone enters, so apologies if any grey boxes appear, but I'll firefight best I can. Yes, thank you, Max, for that intro. I'm going to touch on a couple of things that Max has covered. But yeah, I'm a PhD student at the University of Edinburgh, and I work very closely with the Icelandic company Carbfix. So they are a CO2 mineral storage company in Iceland. So they mineralize CO2 in the basalts out there. And I'm going to talk to you about how we can use certain geochemical methods to actually verify that CO2 storage. So I'll come to that, but first of all, I want to start with a bit of scene setting and a bit of like, why are we doing this? And that ultimately relates to net zero. Now we have quite clear messages coming on a national level and an international level now that doing CO2 storage at scale is an absolute necessity. So the image on the left is the UK Climate Change Committee's net zero report that came out in 2019 and essentially laid the blueprint for our net zero legislation. And it concluded that point source carbon capture and storage, so that's like carbon capture from heavy industry, that's a necessity, not an option, if we're to meet net zero by 2050. And by the same measure, last year, the IPCC in its latest round of reports looked at carbon dioxide removals. So that's things like direct air capture, where you take CO2 directly from the atmosphere and store that. And they also concluded that that is unavoidable if we're going to reach net zero. And the role of CDR is really to counterbalance the residual emissions that are going to be really difficult to get rid of. And that links into what I'm going to talk about today. So I hope some of you have seen a graph familiar to this before. It's again from the IPCC reports, and if I just get my laser pointer up, which I hope you can see, as we go through the century, we will see emissions drop rapidly towards mid-century, at which point they should flatten off at a very low level, but there will still be this small amount of emissions left in the system. Now, if we're going to reach net zero, we obviously have to balance that with removals. And ultimately where geochemistry and other forms of monitoring techniques come in is actually verifying that. And the phrase I like to use is putting the net into net zero. And this comes under the whole topic that's spoken about with increasing frequency in the CDR sector of MRV, or monitoring, reporting and verification. So we need deployable and reliable tools that can enable us to do this and quantify the amount of removals we're doing. So we are doing net zero. We're not, it's not a gimmick. But also another important factor here is, if you think about it, in many ways, CO2 storage is a waste disposal industry. It's kind of analogous to the sewage industry. And that means we're going to need, as these two articles are picking up on here, significant or substantial business models that enable it to happen. So the example at the top here is from Time magazine. covering the Inflation Reduction Act in the States last year, which is going to allocate up to $65 per tonne of CO2 stored for CCS and up to $185 for direct air capture. So that's a lot of state money going on the line there. And this FT article below is covering the world's largest direct air capture plant in Iceland called the Orca project, which captures atmospheric CO2. And the carbon credits for this sold around $1,000 per tonne of CO2 captured. So there's a lot of private and state money being put into this, and essentially having our verification tools, it is the evidence base for these business models, which are going to require a lot of capital. So it's really important. So that's the why. The how, I'm going to give a bit of a brief overview on the different types of CO2 storage, and then get into the geochemical verification means. So as we was hinted at a few times in Max's talk, and I'm sure many of you will be familiar with the kind of traditional clastic or sedimentary form of CO2 storage, where you're either using some sort of impermeable structure like a cap rock, or the actual pore space in a sedimentary rock to store supercritical CO2. And essentially you're using those physical trapping mechanisms to contain the CO2 in the rocks. So it's physical trapping, and because of the difference in density of CO2 to water in the rocks, we can use geophysical monitoring techniques like seismic time-lapsing and things like that. And the classic example of this form of CO2 storage is the Sleipner field in the Norwegian North Sea that's been injecting CO2 since the late 90s. I'm not going to focus on that. I'm going to focus on geochemical or chemical trapping of CO2, sorry. And the key difference here really is rather than containing CO2 buoyancy, as Max explained, you're essentially eliminating the buoyancy by, first of all, dissolving it in water, creates a dense fluid that sinks in your storage reservoir, and then, as Max said in detail, it starts to react with the rocks that you've injected it into and immobilize the CO2 in carbonate minerals. So it's geochemical trapping of CO2. We then, because we don't have that density difference with the CO2 that you do in a physical storage reservoir, we need other forms of verification. So geochemistry can help us there, as I'll explain in a minute. And a classic example of this happening on a field scale is through Carbfix. So Carbfix, as I said, they're based out in Iceland, and what they do is they take all of the abundant basalt that's out there, that's packed full of calcium, magnesium, and iron, our divalent cations that we need. They then dissolve CO2 in water to create sparkling water or carbonic acid, that then, once injected, reacts with the basalts, as Max explained, and pulls out these cations. And then ultimately you end up forming your different carbonate minerals here. Now, Carbfix have field tested this technology over the past 10, 12 years now, and the key step for them, beyond lab experiments, is they need ways of monitoring and verifying what's happening to their CO2 in the field. So traditionally what they've used, and this was first tested on the field scale in 2012 when Carbfix injected about 250 tons of CO2 into the basalts out in Iceland. And they use a mix of reactive and unreactive traces. So the reactive traces that they use, they will measure the dissolved inorganic carbon in the water, or DIC for short, and occasionally they will do spikes of the CO2 with radiocarbon, and then they will co-inject that with an inert tracer, something like sulfur fluorohexide, essentially any inert fluid tracer that should not be affected by these reactions that are happening in the subsurface. So what then happens is you form your carbonate minerals, the white stuff here in the basalt, and then the CO2 and the radiocarbon is sequestered into those carbonate minerals, and then your remaining fluid has lower CO2 or carbon content, but the same as the inert tracer. So in principle, it's pretty simple, and this was the main basis, or the initial basis, for what Carbfix did. As I said, it was around 250 tons injected into the basalt, and using that method and a few others, they found that over 95% of that, approximately 250 tons, was mineralized within 2 years. So, and in terms of how that looks in data form, if I can get my controls to work again, so these were the data from that result. On the x-axis here, we're going from left to right through time, and on our top y-axis, we've got our dissolved inorganic carbon, and on our bottom, we've got our radiocarbon. The black circles here, they are what we would expect to see in the monitoring wells if nothing happened in the subsurface. There was no reactions. I should also say the two grey areas are the periods of injection. And then what was actually measured and monitored was these open squares. So as you can see, the concentrations are much, much lower, and they derived this over 95% figure within 2 years. So that was kind of lift off for Carbfix, and they've had several projects that are ongoing and in development since. But that method of combining reactive and unreactive chemical traces is the bedrock of this document, which that you can find at this link here. This was published last September, and it is essentially the methodology for how they do the geological storage that they do. And this links back to the MRV point I was making at the start. It's essentially not just the scientific framework, but technically the legal framework for how you account for the carbon that you're sequestering, and that then feeds into all the financing and everything. So it's a really important foundation of this document. Now, where my PhD comes in is hopefully adding to documents like these in the future, where we are tracking the CO2 injection using natural inherent isotopes. So we're not adding anything to the water, we're using the isotopes of CO2, water, and noble gases. So today I'm just going to focus on two of them. I'm going to focus on carbon isotopes and noble gases. For anybody that isn't familiar, an isotope is just chemical elements of the same element but slightly different atomic weight. And the reason that's really useful for us here is anytime there's a reaction in the subsurface, so for example when you are mineralizing CO2, the ratios of those isotopes, so for carbon it's 12 and 13, they will reorganize themselves by specific and predictable amounts that we can then use and read into and use to quantify how much of that reaction has happened, i.e. how much CO2 is mineralized. So they're really useful for determining things like that. Now, noble gases, on the other hand, are incredibly unreactive. So essentially what we have here is kind of the same blueprint that Carbfix have: a reactive tracer, our carbon isotopes, and an unreactive tracer, our noble gases, except the difference here is we're just using stuff that's inherent. We're not adding anything to the water, we're just using the inherent chemistry of the CO2. So I'll take those two methods in hand, explain them separately, and then how we use them in combination. So same scenario, we're injecting CO2. It will have a ratio of a carbon isotope ratio, so a ratio of C13 to C12 that we can measure at the start. It's obviously a mix of carbon and oxygen. We then form our mineral, our calcite, at a certain temperature. I've just picked the example here of 50 degrees. And at that temperature, the heavier isotope of carbon, so carbon-13, is preferentially taken into the mineral. And the simplest way to think of that, it is more complicated, but essentially, if something is slightly more heavier, it's thermodynamically more efficient for the heavier phase to end in the immobile phase. So the heavy stuff gets put in the sink, just like something settling out at the bottom of a stream, I guess. So what that then results in is any remaining CO2 is enriched in your lighter isotope. So that's carbon-12. So the CO2 in the monitoring well should be isotopically lighter than what goes in. So that's the basic principle of carbon isotopes. In terms of noble gases, so I said that they're incredibly unreactive, which makes them a very useful tracer for anything in the subsurface. But the other thing that makes them really powerful is that they have three distinct sources in subsurface fluids. So we have magmatic or mantle gases, and that's generally helium-3, and that's the one I'll focus on in a minute. We also have crustal noble gases, so they are the noble gases that are produced from the radioactive decay of minerals in rocks. So that can be used to date groundwater and things like that. And then we also have our atmospheric noble gases, so they enter the system through aquifer recharge. So not only are they very good at being an unreactive tracer, they're actually very good at being fingerprints for where gases have come from and how long they've resided in the crust. So they have several uses. And the real novelty of what we're trying to do here is when we combine the two of them together. So at the site I'm working on my PhD, the CO2 that we're testing this on is actually geothermal. So it's magmatic, which means it comes along with helium-3. So again, we're injecting our CO2 that has a carbon isotope ratio that we can measure at the start, and also a CO2 helium-3 ratio that we measure at the start. So then we go along and we form our carbonate minerals once again at the same temperature. our C13 is once again taken into the calcite mineral. So we not only enrich our remaining CO2 in the lighter isotope of carbon, carbon-12, but also the CO2 helium-3 ratio drops because we've lost CO2, but the helium should be unaffected by this reaction. So we've got two independent trends there that we should be able to measure and use for verification purposes. Now, what that looks like in data or graphical example, what I've done here is these numbers are entirely hypothetical. I've essentially made them up just for illustrative purposes. So we have an injected CO2 that has a CO2 helium-3 ratio that starts at 100 and a carbon-13 to carbon-12 ratio of around 15. And if we're doing, as we've said on that slide before, we should drop our CO2 helium-3 ratio and we should decrease our carbon isotope ratio. So ultimately, we end up with a mineralization line that looks something like that. And essentially, the distance along that line will correspond to a fraction of the CO2 that's mineralized. So we can use it to quantify the mineralization, and the slope of this line will change depending on the temperature that reaction is happening at. So that's how we use it in practice. I appreciate that's quite high level, but I didn't want to blow people's minds with going to a deep dive of isotopes on a lunchtime. So just to wrap up for any of the engineers or anybody that likes field work, this is just a picture of me sampling from Iceland. So this is a geothermal wellhead at one of the power plants. In this pipe, you have the single phase fluid that's produced out of here and goes to the power plant. When we are sampling, we separate the steam out of the fluid. So usually the steam on these wells is about 20% of the overall mass of what's produced. I'm then sampling the condensed steam. So the steam comes through here, goes through a cooling coil, and then we get our condensed steam in this little bottle here. And we have a second separator on here that basically what happens is the non-condensable gases, or the dry gas, go through here. So that includes the majority of the CO2 and the noble gases because they're incredibly insoluble. And then we sample it in these copper tubes here that is just leading into some water to ensure we have no atmosphere backflow. So that's how it works a bit more in practice. It's not super high tech, but it was good fun. So just to wrap up, my take home message is linking back to the start, that we need these reliable and deployable MRV techniques for all forms of CO2 storage. And ultimately, I would quite strongly argue that natural isotopes, so these things here, can be an absolute key method for this, particularly when we're chemically sequestering CO2. So that's really all I have to say. Just one final thing to say that these methods have been used by others and was really led by my supervisor, Stuart Gilfillan, here at Edinburgh, who looked at using these methods on more traditional CCS reservoirs, so gas fields and natural CO2 fields, and did the same quantification means. And Rory, one of my colleagues as well, has also done some more work on that. So there's plenty of other examples of this work out there that are more traditional, not less igneous, if you like. So if you're interested, check that out. But I hope that was interesting and not too general. But I'm happy to take any questions if there are any.
Brilliant. Thanks, Chris. I thought that was very, very clear presentation. It's a nice looking technique that for doing your tracing and your monitoring. So thanks very much. Please keep your questions coming for both Chris and Max in the chat function. I'm going to start with a question for you, Chris. That is around sort of, given that the storage mechanism in the sort of basalts is mineralization, and there's the concern, as we've heard in both yours and Max's presentations, about those near wellbore effects of geochemical reactions. How do you assure that you're not going to get sort of a loss of injectivity in your near wellbore?
Yeah, this
Not
actually,
sure it's possible.
well, yeah, I don't think, yeah. Well, I think this actually links back to something that Max was saying a little bit about the timing of the reactions. So all of the field data, so the kind of number one field evidence that Carbfix have that this isn't a problem for them yet, at least, is that, so they've been injecting now in a separate project from the power plant, they've been injecting 12,000 tons of CO2 per annum since 2014, I think, and they haven't had any loss of injectivity at that scale. Now, it's still a pretty small scale compared to what we need for CCS. All of the modeling that I've seen, and again, it's not really my thing, but what it suggests is that initial dissolution of any existing carbonates and the silicate material that happens closer to the well bore, and you've got to remember that the site that Carbfix are doing this on at the moment has very strong through flow in terms of the fluids. So that dissolved material is carried away from the injection well, and the mineralization then happens, number one, away from the well. So you're talking, a couple of at least a kilometer away from the initial injection point. But also what they found is because you have these essentially like highways of really high velocity fluid flow in this particular fractured system, all the mineralization happens in the lower velocity zones, kind of on the periphery of the flow network. But that is a very specialized system, and I think the plan with mineralization in basalts is to scale it up to huge scale, right? Carbfix are building a port in Iceland that wants to be receiving and injecting 3 million tons by early next decade. So these questions are going to become front and center. So there's a lot of work on if you're mineralizing carbonates, do you induce a microstress on the rock that propagates the fracture network? So it's absolutely not a closed book in terms of answering these questions, but there's a lot of work going into it.
Very interesting. Thank you.
Yeah.
I hope the chat function's still working. I think Max, you've lost your chat history, but there was some questions earlier.
I've got a few. I've got a bit now. I think I answered most of them directly in the chat. But I just on the near wellbore dry out. I mean, I didn't have a chance to really put too much meat on the bone there. But you can use different modeling techniques. I mean, Tough is the one that's been used historically to do 2D and 3D models. And what we're interested in is how you can implicate the results of those studies into your models. So your sort of full-fledged compositional models, and you can sort of generate your KH, your skin, and your loss injectivity. And if you can anticipate that, you can plan for it, and you can do something about it, right? It can be another uncertainty factor. What a lot of projects have done, and the rest of that, the endurance work that I showed, but the rest of it is actually what happens if you flush it with water, because of course the salt dissolves in the water, and then the water goes elsewhere. It gets pushed back by the CO2. So you can mitigate it in some ways, and you can reduce that permeability and porosity decline, as it were. But it's just about integrating those sort of workflows into what we're usually doing, and that just takes a completely multidisciplinary approach that a lot of people you always talk about the energy transition skills, etc., is sort of one of the things you have to be ready to integrate different disciplines, as it were. And I think that's quite a fun thing as a chemist or a geochemist, is that you are forced to work with fluids as well as the rocks, which gives you a little bit of cross-cutting.
Yeah, very good. And in terms of the transferability of the methodology, Chris, you spoke in terms of for siliclastic systems, it's seismic monitoring, and for basalt systems, it's geochemical. But is there any reason why we couldn't transfer some of these geochemical techniques across to the clastic world?
Well, I mean, you need to be able to sample the reservoir fluid, and I mean, I've only done limited work on clastics, but my understanding is one of the biggest risks in a clastic CO2 storage reservoir is the wells. So, in an ideal world, you're not having to go into the reservoir. That said, there definitely is, and this is where Stuart and Rory's papers that I highlighted at the end, they do this. So they quantify the amount of CO2 that's dissolving in these big CO2 CO2 fields and gas fields, and it's not an insignificant trapping mechanism at times. Some of these fields show 20-30% of the CO2 that's in place, of which at times is on the order of tens of millions of tons, is dissolving into the reservoir fluid. So yeah, you can apply them. I think for verification, ultimately the key objective is containment. So long as you can demonstrate containment robustly, then you just use whatever's fit for purpose and the lowest cost as well, I guess.
Yeah, fair enough. And where next, really, in terms of the CO2 storage in the basalts? There's talk about scaling up, but
Yeah,
how do you
I mean,
move this to a more global scale?
number one is trying it in older stuff. So, the basalts in Iceland are very young. They're pretty porous as igneous rocks go. And there are some highly altered areas, but they're not altered in, say, the way the tertiary lavas are in the UK or stuff like that. So trying it in older sequences. And ultimately as well, if this technology is going to really roll out on the global scale, moving to the near shore and also looking to use seawater, because dissolving CO2 in water, Max showed how it's CO2 is more soluble in water at lower temperatures, but even so, Carbfix dissolved their CO2 at 20 degrees, and you need a ratio of about 25:1 water to CO2. So it's very water intense, and if you're then going to do it elsewhere in the world, you really need to be using saline water, because not everywhere is as blessed with water as Iceland and the UK. So.
Got you. And Max, you got anything to add, really, in terms of sort of where some of these geochemical techniques are going to sort of head in the future?
Well, it's interesting. I think a lot of the work that at least I've been doing in the last 3 months, especially on some projects in the Gulf Coast, and understanding the implications of the geochemical implications of injection, especially where you need things like monitoring wells or stratigraphic wells, or very maybe quite far away from your potential injectors, is understanding the implications of, okay, if the CO2 does come into contact with the water around the well, what are the implications of the well? Because that's those are your biotipations, right? This is what you're concerned about. This is what you're changing. This is what you need to manage as a risk, as a great risk, a great expense. And yeah, I mean, it's not that well explored. People say, yeah, carbonic acid is pH 3, and we can cement for pH 3 using Schlumberger CO2 resistant cement, and we can use 25 chrome in our well area to case. But you might not want to spend all of that money, because this is a waste disposal business. Your margins are much lower, so if you have to drill a monitoring well for your class 6 well permit to have a look at the pressure or the plume propagation over time, these things really matter, and we'll see, I think in time to come, where more research and more work is done, that information will be shared and more readily available, and people understand the implications of all of these different multidisciplinary approaches.
Okay, thanks, Max. We've actually have had a question come in from Peter Salisbury, so I will let the session run on a little bit beyond the 13:30. Are the noble gases recovered afterwards? This is a question for Chris, I guess.
Yeah.
For example, helium is a rare noble gas and expensive. Typically, how much of the noble gas will be required for one project?
So I can only speak to the stuff that we've done, and I think, as I said, the helium that we look at is naturally occurring, so it's magmatic. Now, there's a very good point, because helium is very in short supply at the moment. Now I know there is work going on of spiking in much the way that Carbfix did initially. You can add helium-4, different isotope of helium, and other noble gases that aren't maybe as pressured at the moment as helium is to the CO2. But I haven't done anything on that. We just use the stuff that's already there, and it is quite specialized because it's a geothermal environment. But no, it's a really good point, because helium is very expensive.
Really good. Okay, well, I mean, I think that seems to be the questions that have come in. I guess the overall message in terms of his CO2 geochemistry overlooked. I guess the message from both of you would be to say to any project, keep CO2 geochemistry in mind, because it can have serious implications. And is it underappreciated? Well, I think, Chris, you've shown clearly how good use of geochemistry can be a very effective monitoring and verification. So,
Just very, very quickly, one of the papers I showed at the end, Stewart's from 2017, it actually looked at, so it used noble gases to look at an allegation of CO2 leakage from a EOR site, I think in Canada or the States, I can't remember, in North America. And they used some of these techniques to prove that the CO2 that was alleged to be leaking from the EOR project, it wasn't from the EOR project, it was biogenic. So you can use it, you know, in theory, God forbid, but you know, if there are circumstances in the future where we have these allegations of leakage, they can be used to fingerprint things and actually differentiate between what is leakage and what isn't.
That is really, really good to know. Yeah. Okay. Yes, we will be putting a link to the recording of this up on the SPE London website. It probably might take a few days to get up there, and we'll be putting copies of the presentation on there as well. So that just leaves me to say thank you very much to the audience for giving up this sunny lunchtime and sitting in front of your computer to listen to this. Thanks very much to Chris and Max for their presentations, and to OPC for sponsoring today's session.
Thank
So
you.
thanks all.
Yeah, thank you, everyone. Happy to, if anyone wants to email any questions, happy to answer them. Give me something other to do than my job. That'd be nice. All right. Cheers, everyone.
Okay. Bye and thank
Cheers.
you.
See you later.